Hi everyone, this is ITCS 2021 talk on majorizing measures for the optimizer. I'm Makrand and this is joint work with Sander Borst, Daniel Dadush and Neil Olver. The central object of this talk will be Gaussian processes. A Gaussian process is a collection of Gaussian random variables. We will assume that they are centered, that they are mean zero, and they're indexed by a subset X in RD. I will also call this set X the index set throughout this talk. And the central protagonist of this talk will be the expected supremum of this process, which is the expected value of the supremum of any of these random variables. Let's look at some simple examples to make it more concrete. Suppose X is a set of extreme points of a polytope in the dimensions, and Zx is given by taking a standard Gaussian in Rd and taking its inner product with each point in X. The expected supremum of this process is also called the Gaussian width of this point set X, and it is very useful in dimensionality reductions, mathematics, statistics, and so on, and we will see some applications later in this talk. Another example comes from random matrix theory. Suppose A is a Gaussian random matrix, so that each entry of the matrix is independent Gaussian, and X is the set of all points with Euclidean norm 1. And suppose the process is given by this quadratic form x ax. In this case, the expected supremum of this process is the expected operator norm of A, and this has been very well studied in random matrix theory. So from these applications, it should be clear that Gaussian processes are very natural, and they have tons of applications in machine learning, mathematics, computer science, statistics, and so on. So let's look at one particular example that will be relevant for us also, which is dimensionality reduction. And here a very powerful result of Gordon says the following. Suppose X is a subset of the unit sphere in D dimension, then there is a projection matrix that reduces the dimensionality from D to M dimensions, where M is the Gaussian width square, and it preserves approximately all norms in the set X. So this theorem is very powerful, and it's very useful in dimensionality reduction, compressed sensing, and so on. And in particular, it generalizes the well-known Johnson-Lindström's lemma, which probably most of you have seen, where M is taken to be log of the cardinality of the set. And one can show that Gaussian width is always bounded by square root of the log of the cardinality of the set. We will also see this later in this talk. So this gives a powerful generalization of Johnson-Lindström. Given this, one can ask, how can we prove bounds on the expected supremum of a Gaussian process? So a very nice characterization of this was given by Sudakov, who showed that it is uniquely characterized by the following distance metric defined on the set X. So the distance is given by the standard deviation of the random variable Zx minus Zy. And for example, in this very special case of this Gaussian process given by a point set, this metric is exactly the Euclidean metric, but this need not be the case in general. So now we know that this metric completely characterizes the expected supremum. So one can ask, what properties of this metric space gives us upper and lower bound on the expected supremum? So let's first look at some lower bounds. So one can see that the expected supremum is lower bounded by the expected absolute value of the difference Zx minus Zy. And this just follows from symmetry around 0. And this holds for any points x and y in X. And Zx minus Zy is a Gaussian with variance distance squared. So in particular, this gives us that the expected supremum is lower bounded by the diameter of X by taking 2 points x and y with maximal distance in X. So this gives us a very simple lower bound. And here we only chose 2 points, but one can ask, if we chose many points in our point set, then can we strengthen this lower bound? And it turns out that this can be done. In particular, the expected supremum is lower bounded by the supremum over all scales epsilon and times the square root of the log of the cardinality of the minimum epsilon net of x. And by epsilon net, I mean that the minimum size of a subset of x, where every point of x is within a distance epsilon in this metric from each point in the net. So in particular, if we take epsilon to be the diameter, then the cardinality of this set is exactly 2, and we get the previous bound. But this bound can be much better in some cases. So now we have a lower bound in terms of the cardinality of the minimum epsilon net. So what about an upper bound? So let us assume for simplicity that 0 is in the convex hull of our point set and our set lives inside the unit Euclidean ball. So in this case, the expected supremum can be upper bounded by the square root log of the cardinality of the set. And this just follows from union bound over x points and using the Gaussian tail bound of e to the minus t square over 2. And one can strengthen this bound, and this was a very influential result of Dudley, by using a technique called chaining. And Dudley showed that the upper bound can be replaced by integral from 0 to infinity over all scales epsilon, the square root log of the cardinality of the minimum epsilon net at that scale. And it will be very useful for us to see how this works. So let me give you a short proof of this. So let us consider the following layered tree on our point set x. The root of this tree is the origin. The kth layer of this tree is an epsilon net of x, where epsilon is 2 to the minus k, and we add an edge between a point y and a point x in the previous layer if they are nearest neighbors to each other, and we choose exactly one such point. So in particular, the distance between x and y will be 2 to the minus k if y is in the kth layer. So with this tree, now we can prove Dudley's upper bound. So the basic idea is we write our random variable zx as a telescoping sum of zxi minus zxi minus 1 along the edges of this tree. So in particular, xk is the point x and x0 is 0. So this exactly gives us zx. And we know that zx minus zxi is a Gaussian with variance 2 to the minus I squared for every edge. So now, just by taking a union bound over all the edges of a single layer, as before, we get that the expected maximum value attained by any of these random variables zxi minus 1 is at most 2 to the minus I times square root log of the cardinality of the layer I. And this 2 to the minus I comes because of the standard deviation. And in particular, now summing this over all the layers, and using linearity of expectation, we get that the expected supremum is upper bounded by summation of 2 to the minus I times square root log of cardinality of ni. And this is essentially Dudley's bound because this is just a discretization of the integral, and one can show that they are only constant factor away from each other. So we have proved Dudley's upper bound. So this tree that we just saw is a special case of what we call a chaining tree. So I'm not going to define this in general, but I will keep referring to it throughout this talk. So it will be helpful to keep this example in mind. And in the general case, you need to assign edge probabilities and lengths to each edges so that it works with the union bound. So now we can come to majorizing measures. So we saw this lower bound on expected supremum in terms of the cardinality of the epsilon net at a single scale, and we saw this upper bound that was proved by chaining. And it turns out that both of these bounds are not tight. The gap can be arbitrarily large. So motivated by this, Fernique proved a better upper bound, which is called the majorizing measures bound. So he showed that the expected supremum is upper bounded by the infimum over all probability measures mu, the supremum over all points in the set. And now again, there is a similar looking quantity as Dudley's bound, but instead of the integral from 0 to infinity square root log of the cardinality of the minimum epsilon net, here there is a root log of 1 over the probability measure of a ball of radius epsilon around x. So this might look strange at first, but the intuition behind majorizing measures is actually very natural. So in particular, in Dudley's proof that we just saw, all the vertices in each layer of the chaining tree, they were exactly the same. But you could consider putting weights on them so that some vertices are more important than others. And this is exactly what majorizing measures tries to do. So in particular, if the ball of radius epsilon around x has very large mass, then that point x should be more important. And in the end, you just choose the best possible probability measure that you can choose. So this is the intuition behind majorizing measures. So Fermi conjectured that this upper bound was tight, and this was proven by Talleyrand in a very influential result that's now called the majorizing measures theorem. So Talleyrand showed that this majorizing measures bound is tight up to constant factors. So majorizing measures in fact characterize the expected supremum of Gaussian processes. The original proof of this theorem was considered very difficult, and the key insight of Talleyrand was a notion that was dual to chaining trees. So Talleyrand developed a notion of what we call a packing tree. So they gave lower bounds on expected supremum, just as chaining trees gave upper bounds. And since this theorem is very, very important, over the years many simpler and different proofs have been found, mostly by Talleyrand but also by other people. And in this talk we will also give yet another proof of this theorem that we will see pretty soon. So before we do that, it will be very helpful to look at what packing trees are and why they give a lower bound on expected supremum. So the nodes of a packing tree are subsets of our index set X. And each child of a node is also a subset of the node itself. So assuming that the diameter of our index set is 1, we require that the diameter of each node in the tree goes down exponentially with the depth. So it's bounded by 1/2 times that depth. And we also require that the children of any vertex are separated in this tree. So in particular, for any child, Cij, the distance must be at least 1/10 times the depth of its parent plus 1. So essentially, we're trying to pack as many far apart children as possible in this tree. And let me define the value of a tree, which is a very complicated looking expression. So let me try to help you parse it. So this is the minimum over all paths in the tree. The first quantity here is just the diameter of that particular node along the path. And the second quantity is square root log of 1 over the number of children of V. So why do packing trees give a lower bound on expected supremum? This is due to the Sudakov minoration inequality that was also proven by Talleyrand. So Talleyrand showed that the expected supremum over V is at least 1/10 times the depth of V, which is the diameter of essentially that node V, times square root log of 1 over the number of children, plus minimum expected supremum over any children of V. So in particular, the first term here is exactly what that appears in the value. So if you just apply this Sudakov minoration inequality starting from the root inductively, then you will get all possible terms until the leaf. And from this it follows that the value of any packing tree is a lower bound than the expected supremum of the process. And we also saw that the expected supremum is upper bounded by the value of any chaining tree. And let me define this quantity gamma 2, which is just the majorizing measures bound, and essentially the minimum value of a chaining tree. So the expected supremum is lower bounded by packing tree and upper bounded by gamma 2 over the value of a chaining tree. And the key insight of Talleyrand from this majorizing measures theorem is that the maximum value of a packing tree is exactly equal up to constant factor to the minimum value of a chaining tree. So there is some kind of strong duality between chaining and packing trees. And this basic statement, this is not very obvious in previous proofs. So for example, in Talleyrand's original proof, he proved that there is a packing tree whose value is lower bounded by gamma 2, which implies the statement in a later proof, he showed that there is a chaining tree which gives a lower bound on the value of the process, which also implies this statement. So in these proofs, what belongs to the process and what belongs to the matrix are entangled in complicated ways. So now we can revisit majorizing measures theorem as follows. So we can break it down into two parts. The first part says that the value of the expected supremum is lower and upper bounded by chaining and packing trees. And the second part is that the maximum value of a packing tree is same as the minimum value of a chaining tree. So there is a combinatorial min-max theorem or strong duality for the underlying metric space between chaining and packing trees. And the majorizing measures theorem is just the consequence of these two statements. So in particular, this way of formulating this, it separates the role of metric from the Gaussian processes. And now I can describe what our main contribution is. We give a new constructive proof of this combinatorial min-max theorem using convex duality and rounding. And our main insight is that this strong duality between chaining and packing trees, this in fact stems from a convex program that lurks in the background. So this is in fact a consequence of convex duality. So in particular, our proof works completely in the setting of metric spaces. So before I can say more about the proof, let me first try to give you some nice applications. So since we can solve a convex program and do some rounding, this gives us deterministic polynomial time algorithms for computing various different things. So in particular, we can compute optimal chaining packing trees labeled as admissible nets in deterministic polynomial time. This also gives us yet another way of computing cover times of random walks. This was already shown by Dingley and Perez. And this gives us a way to compute the projection matrix in Gordon's theorem. So this requires deterministic construction of optimal admissible nets and builds on a previous work of Dadush, Guzman, and Olver, and a chaining-based proof of Makrand and Sultan Kotabi. So let me try to say a little bit more about where the convexity comes in. So let's look at this gamma 2 functional, which is just the majorizing measures bound. So this is essentially a convex program because root log 1 over p is a convex function when p is between 0 and 1 over e. So now there is a technicality that the measure can take value between 0 and 1, but this is just a technicality that I will show you how to fix in a second. So now a primal measure mu, that is a solution to this program, you can round it to chaining trees. And in particular, this was already shown by Talleyrand in 2001 in his Majorizing Measures Without Measures paper that introduced the concept of generic chaining. We show that this rounding can be done in nearly linear time, which is x squared, since you need to specify all pairwise distances for an arbitrary metric space. So now we show that any dual measure for a simplified dual, it can be rounded to a packing tree, again very fast in nearly linear time. And just by a consequence of convex duality, we get that the maximum value of a packing tree and minimum value of a chaining tree, they are equal up to constant factors. As a final remark, let me mention that rounding is in fact the hard part of this proof. Going from trees to measures is very easy. For example, if you have a packing tree, if you just take each children uniformly at random and keep doing this until we hit a leaf, the probability measure that is induced on the leaves, this exactly gives you the value that is achieved by the dual. So in fact, we are doing the hard direction by rounding a measure to a tree here. So let me tell you now how to fix this annoying technical issue that this is not a convex program exactly. So for this, let me replace the root log 1 over p with another function h. And one has to remember that root log 1 over p was just the approximation of the Gaussian tail, where we use the simple tail bound of e to the minus t square. But instead of that, one can use the Gaussian tail itself. So one can define h of p to be the minimum x such that the probability mass of the Gaussian tail is exactly p at that point. This function is convex and decreasing on the whole interval 0 to 1, so this fixes this annoying issue. And now one can work with this more general function gamma h, which is convex. And in particular, if one replaces the Gaussian random variable g with a arbitrary symmetric log concave random variable, everything in our proof still works. So this works for a more general class of densities than just Gaussians. Okay, so now we have our convex program, which is the primal. And let me define a very similar looking dual program. And this is not a real dual because this is not even concave or convex, but here nu is supposed to be another probability measure, and I've swapped the maximum and minimum here. So and the main result of our paper is that the value of this primal and the simplified dual, they can be at most a factor of 2 apart, ignoring some additive factors of diameters of x. And this also answers the question of Mendel and Auer, who showed the same relation but with a fairly large constant, but they did not rely on convex duality, and the proof was fairly complicated, whereas ours is quite simple. Okay, and now one can get primal and dual measures just by solving a convex optimization problem and some simple greedy algorithm. And then to get optimal chaining and packing trees, you can just apply some rounding algorithms, which I will tell you about later, to get chaining and packing trees. And this gives a constructive way to prove the majorizing measures theorem. So the rest of this talk, I will tell you the main ideas involved in proving the ski lemma. In particular, the first step is to notice that instead of the maximum over all points in X, one can again replace it maximum over all probability measures nu, where nu is a different measure now, since this does not change the value. This one can do because you're optimizing over the same convex hull, essentially. And now one can swap the min and max from there to get the real dual, and convex duality implies that the value of this dual is the same as the value of the primal. Okay. So now this dual looks much more complicated because there are two different probability measures, mu and nu. But one can ask, what happens, what's the minimizer mu look like there? In particular, what happens if one sets mu to be the outer measure nu? If one does that, one gets another optimization problem that we call the entropic dual. And in particular, since we substituted mu to be nu, the value of this entropic dual is at least the value of the real dual, but we show that this cannot be more than a factor 2 apart, up to some additive factors. And the last step is to reduce this entropic dual to simplified dual, and here the only difference is the bottommost dual doesn't have the expectation but instead a minimum. And again, one direction is clear, the minimum is at most expectation, but we also show that replacing the expectation with the minimum doesn't change the value too much, up to a constant factor of the diameter. So altogether, this sequence of simplifications, the last two sort of implies that the value of the real dual and the value of the simplified dual at the bottom, it can at most be a factor 2 apart. And by convex duality, the value of the primal is the same as the value of the dual, so we get our key lemma. So now let me say a few words about how to prove this very nice approximate duality statement that setting mu to be nu there and that real dual does not cause too much error. In particular, we are going to show that for any outer measure nu, if we take mu to be nu, then the value can differ by a factor of at most 2. So the left hand side here exactly gives you the value of the entropic dual, and the right hand side gives you the value of the actual dual. And this statement, this claim, still involves an integration over various scales epsilon, and we are going to even fix a scale epsilon, and on the left hand side look at a ball of radius 2 epsilon, and on the right hand side look at a ball of radius epsilon and show that these values differ by a constant additive factor. And if you integrate over various scales epsilon and do a substitution of 2 epsilon to epsilon, then you recover the claim on the top. So to prove this, it will be useful to view this in a graph theoretic way. So consider the graph, bipartite graph, where the left and right hand side are just elements of x, and there is the edge if the distance between the 2 points is at most epsilon. And this is a weighted graph. On the left hand side the weights are given by nu, and on the right hand the weights are given by mu. Now if you consider a point x on the left hand side, its neighborhood on the right is exactly the ball of radius epsilon, and its 2-hop neighborhood is exactly the ball of radius 2 epsilon. And essentially what we want to show is that transporting the mass from 1 to 2-hop neighborhood, it doesn't incur too much cost. So in particular, let us consider a very special case. Suppose it happens that for every subset A on the right, its mu measure is always smaller than the nu measure of its neighborhood. And this is exactly Hall's condition, and this is saying that there is a fractional perfect matching between mu and nu. So essentially we can match with all the probability mass of mu and nu. And in this case the proof should be very simple. I mean, you just divide and multiply by the same quantity, and we just use the very basic property of this function h, that it's submultiplicative. And if you just use that, this ratio is at least 1 by our assumption, so just using submultiplicativity gives us that this is bounded by this quantity. And this is essentially the claim, and h of 1 is even 0 by our assumption, so this gives us the claim in this very special case. And in general, if this is not true, and if there isn't a fractional perfect matching, then we cannot match the entire probability mass, but we can still match some beta fraction of the mass where beta is less than 1. And now the basic idea is we just do this, remove the maximal blocking set, and keep repeating this process. And in the end one can show that you essentially incur a cost which is given by maximum over the unit interval of some quantity related to h that we can bound by a constant. So this is essentially the proof of approximate duality. So this proves the first statement. So for the next statement, where we replace the expectation with the minimum to get to the final simplified dual, I'm not going to go too much into it, but the basic idea is very simple. One just iteratively removes the values where minimum is much smaller than the expectation, and then replaces the original probability measure with the condition distribution. And one can show that this gives you another dual measure where the value of these two things are very close to each other. So this proves this approximate duality statement, and now one has a way to find these primal and dual measures just by solving this optimization problem and by simple conditioning that can be done using a simple greedy algorithm. And this gives a way to compute optimal chaining and packing trees by rounding. So let me say a few words about rounding also, just to give you some idea of how it's done. So again, the rounding is done by a procedure called greedy-bound partitioning that was introduced by Talleyrand. So the procedure is very simple on an intuitive level. So this is our index at x. We just repeat the following until we exhaust all the points of x. We take the measure of a ball of a given radius, we remove the ball of a larger radius, and we do this again, and we keep doing this until we exhaust the whole set x. And it's not important that we are maximizing measure over balls. You can consider variants where you, instead of balls, you replace them with intersected balls, instead of measures here, you can maximize some other potential or functionals over your space. But the basic idea is this. And then we recurse and geometrically decrease this bound. So this is the basic greedy ball partitioning. And the previous rounding to packing trees, this was based on a variant of this greedy ball partitioning. So in particular, there one does not round from measures, one needs some functionals that satisfy certain property. And instead of maximizing measures or the value of the function over balls, you look at intersected balls. So this is a little bit asymmetric compared to the primal rounding, where one just maximizes the measures over balls in a very simple way. And also because of the intersection, it's difficult to implement this in near linear time. So our main contribution is that we show that greedy ball partitioning, if one uses primal and dual measures, it gives you chaining and packing trees in a fairly symmetric way and in near linear time. So in particular, given an input measure rho, we can get chaining and packing trees that achieve the value attained by the corresponding primal and dual programs. And also, the algorithm is fairly symmetric. In particular, the induced partition that is given by the outer balls in this greedy ball partitioning, this gives us a variant of chaining tree. And the inner balls, which are already separated, a large subset of them gives a packing tree. Of course, I'm simplifying a lot of details here, and the analysis is still quite subtle and involved, but at least this makes the primal and dual side fairly symmetric. So let me summarize and conclude with some open problems. So we gave a new constructive proof of the combinatorial min-max core of the majorizing measure theorem. Using convex duality and rounding, we showed that the value of the primal and the simplified dual are at most a factor 2 apart. One can round these to find optimal chaining and packing trees. So the most costly part of this current picture is finding these measures. For now, we just relied on a black box solver to solve these optimization problems, and the runtime depends on rectangular matrix multiplication. But even if you can do it optimally, it's probably hard to do it in a general way in near linear time. But since we want to solve a specific convex program and we really need a crude additive approximation, one can hope that you can still do it in near linear time, even finding the primal and dual measures. And the second thing is chaining has various algorithmic applications, and whether one can find, using this convex optimization paradigm, some other algorithmic applications of this approach. So that's it. Thank you very much.